So here we are, thermodynamics. We get to revisit this topic once more, and I gave you a little bit of a taste for it when we talked about the lattice enthalpy analysis in terms of solubility of salts. But this time we're going to go the entire way through explaining the full extent of thermodynamics. So we're going to start by talking about heat and work. As you may already know by now, the energy difference between products and reactants is what we ultimately associate with thermodynamics. And it tells you to what extent a reaction is likely to happen. Doesn't address the issue of whether it's going to happen fast or slowly, but it tells you whether the reaction is going to happen on its own or not. So one thing that you have to remember in order to make sense of what we're about to talk in thermodynamics is that heat is determined by the mass of the substance multiplied by the specific heat of the substance times the change in temperature. Alternatively, you could be multiplying the moles of a substance by the heat capacity at constant volume or constant pressure, and whether you're dealing with a specific heat capacity or heat capacity at constant volume or pressure determines whether you use the mass or the moles of the substance to carry out the calculation. One thing that you will see me do a lot in the context of deriving the thermodynamic parameters is looking at the changes in heat, specifically changes in heat per mole of substance. So if you divide both sides of the equation by number of moles, and simply add the letter D representing change, the change in Q per mole is going to be equal to the heat capacity at constant volume times the change in temperature, or the change in heat per mole will be equal to the heat capacity at constant pressure times the change in temperature. So it's something you're going to see me use quite a bit. Another thing that you may have looked into, or maybe not in the past, is the fact that work, the change in work, which is another form of energy, is basically energy that is used to perform some type of activity that may not necessarily happen on its own. But the work is given by the formula negative P times the change in volume. This is from the point of view of gases. So this is work that gases could actually perform upon changing their volume. If the pressure is constant, then automatically the work itself is determined by the negative of the pressure times the change in volume, V final minus V initial. But if the pressure is variable, then you actually have to use the following formula to find out the work. Negative moles times the gas constant times the temperature in Kelvin times the natural log of V final over V initial. These are things that you may have seen in the past when you discuss thermodynamics for the first time. In this class, I'm not going to actually have you calculate heat and work anymore because the only reason I'm introducing it here is so that you see where the derivations that I'm going to apply to come up with the new thermodynamic parameters come from. Alright, so specifically, everything eventually boils down to the first law of thermodynamics. And the first law of thermodynamics in equation format tells you that the change in internal energy is equal to the change in heat plus the change in work. And the first law of thermodynamics basically tells you that the energy is conserved. You neither create it nor you destroy it. And what that basically means is that the internal energy is actually constant. You have a constant amount of total energy. And that energy can be distributed into heat or work to whatever extent. As long as the addition of these two things yield the internal energy, you can basically transform all the heat to work or all the work to heat and vice versa. Alright, so this is the first law of thermodynamics, and this is the equation that I'm going to utilize to derive all of the thermodynamic parameters. And specifically, notice this, the change in work, I'm replacing automatically with the negative pressure times the change in volume. So I'm going to be doing that a number of times throughout this lecture, so just be aware of that substitution. Another thing that I also want to point out is that the work and the heat, for that matter, they are actually path dependent. So in this little graph right here, if you go from a state of 1 atmosphere pressure and 1 liter volume, ultimately to a state of 2 atmosphere pressure and 2-liter volume, you could do this a number of ways. You could go first in this pathway in which you increase the volume first, but you keep the pressure constant, and then you change the pressure. Or conversely, you could first change the pressure and then change the volume. Or alternatively, you could do both at the same time and go directly to the endpoint. And depending how you choose your path of attack to get to the final point from the initial actually dictates what the value of the work is going to be. And it does change depending upon what path you take. Now, that is an inconvenience associated with work and heat. Because ultimately, when it comes down to chemistry and physics for that matter, we want to deal with values that are constant irrespective of how we approach them, right? Because if the path depends or allows the ultimate answer to change, then you being in a different city at a different altitude with different temperatures will change the entire result altogether, and you will never have consistent results. So what we try to do is to change the path-dependent functions, the heat and the work, into path-independent functions, which is technically what the internal energy is, because it's a constant, right? So it doesn't really matter how you go about finding the energy for the internal energy. That will remain constant throughout. So we're going to use that whole premise of taking the path-dependent functions of heat and work and manipulating them mathematically to turn them into expressions that are path-independent. And that's how we end up deriving the enthalpy. So I'm going to show you that before we move on to the next section of the video. Okay, so the way we basically trick the system into becoming a path-independent function is to subtract the changing work from both sides. So we have internal energy minus dW, which is the same thing as saying internal energy plus PdV equals the changing heat. And what that would basically do for us is to say that if we are solely looking at the changing heat, this can provide us a means of making the heat path independent. Now, the way that works out, though, is in a very specific manner, because for this to be truly path independent, then that means that the combo of internal energy, pressure, and volume, which you have right here without the changes, has to be basically continuous throughout. And this is a little addendum showing you how to perform differential equations technically. Specifically, you apply the change to each one of the functions right here. And it's very similar to what you do with multiplication. You simply apply the change to the function, except that for differentials, which is kind of what the change represents here, you have to apply it to each individual function one at a time. So that means that we apply the change to u, so we get du. And when we apply the change to PV, we have to do this one at a time. So we first apply the change to P, so we end up with VdP. But then we have to apply the change to V as well, in which case we end up with PdV. And what you see right here is that applying the change to the functions alone, which will make this whole thing path independent, requires that you have du plus VdP plus PdV in your expression, which is clearly not what we have in the first law of thermodynamics, one of the reasons why the heat is not path independent. But there's one way to trick the system, the equation, into turning into path independent function. As long as you apply the differential to internal energy plus pressure times volume, you have to have the following setup that we have here on the right side. But notice that you have change in pressure multiplying by volume, which is the only thing that doesn't appear in the first law of thermodynamics. Since this depends on the change in pressure, the way you can trick this equation into equaling the first law of thermodynamics is to simply keep the pressure constant. If you do that, then VdP automatically vanishes out of the equation. It becomes zero because if there is no change in pressure, the change in pressure is equal to zero. And so, at constant pressure, the change to UPV is literally equal to the first law of thermodynamics, which means that at constant pressure, the heat is actually path independent. You can approach it every which direction you want, and the heat will be guaranteed to equal the same value, no matter where you perform the experiment, no matter what you do to get from point A to point B, as long as you start at point A and end at point B. So we call the differential of U plus PV the enthalpy. So this is the changing enthalpy, which equals the changing heat. So this is the first path independent version of heat, and this is what you've observed in your previous chemistry classes. Um, and so the enthalpy is simply heat, but it's heat that is path independent. This is what we refer to as state functions, functions that do not depend on the path that you take to go from point A to point B. And mathematically speaking, this has a relationship that involves the differentials where you have multiple functions present, so you have a 3D function here, and whether you perform the differential with respect to x first and then y, if this is to be a state function, should be the same as taking the differential from y and then x. And this is something known as a Maxwell relationship, but that's more differential equations than anything else. The next thing that I want to discuss in regards to enthalpy, just as a refresher, is the different methods that you use to find out the enthalpy of a reaction. You could use heats of formation, you could use Hess's law, or you could use bond dissociation enthalpies. And the ones that I'm going to focus on exclusively in this set of lectures are the heats of formation and Hess's law. Alright, so I will stop the video at this point, and in the next video we're going to look at how we calculate the enthalpy for using the enthalpies of formation values and using the Hess's law cycle. And from then on we'll move on to the next topic. So see you in the next video.